How will this work? My name is Robert Pagan, and this is my at-home lab 11, section MO3, with Greco, Physics 2211. So for this lab, we got to do our own model, whatever we wanted. We just had to use physics to support whatever conclusions we came to. I decided to, I calibrated the stick to this pole here, which I determined to be about 12 feet based on like the height of the children. And so then I went ahead and plotted or used his like center where the swing actually touches his body as the center of mass, and I went ahead and plotted that. Yeah, and then I used the code from the previous lab, but what I changed was the initial position of the ball of mass and the spring stiffness, and then I just used force of gravity, just like in an actual swing set. And so let's see, right here, mass of the ball about 66 kilograms, which is a fair weight for a child. And then the position vector I put to close to where the kid looked at in the video. And then I loaded my CSV data, but there was errors and like the graphs wouldn't even come up, so I just commented that. And then we have the gravity, and I determined this value of K just kind of through guess and check like we did with the last at-home lab, and you'll see the model is pretty similar to the actual video. And same way we calculated L sub 0, S, and L hat, and then I created arrows to model the perpendicular and parallel forces, as well as just net force, the direction of it throughout the entire video. And so here we have the video, if it runs, and okay. And so the red arrow is perpendicular force, blue is parallel, black is F net, which is also the direction of momentum. Okay, and so in this model, as you can see already from the video, with just the force of gravity and force of the spring, which no matter how taut a chain is, it still holds the same properties as a spring. So in this video, you see that it keeps swinging, and it swings to the same points that it starts and ends at. Essentially, no energy is lost in the swinging motion. And I'm going to go ahead and just show you this. I said at the beginning what we were doing, but so you can see it, model swinging of a child on a swing set. And what we learned, what I'm getting to now from the video, if friction didn't exist, energy would not be lost to the system, and the child would drop from a point and swing back and forth perpetually. So as the video showed, and as this principle, delta P system equals 0, shows, the child should swing back and forth forever. In the video, he does, but that's because he swings his feet back and forth, adding force at both ends of his path. And so if he stopped swinging his legs, he would eventually swing to shorter distances and stop swinging altogether, because of the friction of the axle. We also use delta P equals F net delta T, F spring, and, to determine F net, and this showed us the arrows. Okay, so it means that the swing should keep swinging according to the model. It doesn't happen because of dissipation at the axle. Energy is lost to friction, the center of rotation, the swing axle, and the swing in the video keeps going because force is constantly added by the swinging legs. Already told you all that. And so what if there was no friction in the video and in real life? Well, he would keep swinging forever. He would have to be dropped from a point or get himself up to a certain point with his legs, and then he could keep swinging at that point, have the same exact path, and reach the same exact points forever. What if force of friction was added to the model? That was included in F net. the swing would eventually come to a stop, and the model would gradually swing shorter and shorter distances. And that's my Lab 11. Thanks, guys.